Hello, AP Chemistry students. This is section 3.5 on kinetic molecular theory. Our learning objective here is to explain the relationship between the motion of particles and the macroscopic properties of gases with A, the kinetic molecular theory, B, a particulate model, and C, a graphical representation. So kinetic molecular theory is all about relating the temperature, pressure, and volume of a gas to how much kinetic energy the particles and or molecules have. So we know that gas molecules are in constant motion and collide with each other in the walls of the container. That's how they exert pressure, and they do so without losing energy. So these are called elastic collisions in physics. And we know that the kinetic energy of a gas is directly proportional to its absolute temperature in Kelvin, because we talked about how temperature is basically equal to the average kinetic energy of the system. The higher the temperature, the higher the kinetic energy of the particles. That's what's being shown here. Another thing to consider is the kinetic energy formula from physics. We know that kinetic energy is equal to 1/2 mv squared, where m is the mass of a particle and the v is the velocity of the particle. So even if two different particles have the same kinetic energy, they're not necessarily going to move at the same speed, the same velocity if they have different masses. You can think about like having two marbles that you roll down a hill. If one is more massive than the other, they're going to have a different overall speed. Now, we know that gas molecules at a specific temperature will have the same amount of kinetic energy, regardless of the element or the molecule, but the mass of that molecule will affect its velocity. So if we look at this equation, since the product of mass and volume equals the energy, they are inversely proportional. So as the mass of the particle goes up, the velocity of the particle is going to go down if we have the same kinetic energy. This means the more massive a molecule or atom, the slower it's going to move at the same temperature as other things that are less massive than it. So let's look at some graphs to kind of get a handle on this. So this is something called a Maxwell-Boltzmann diagram. These are something you might see on the AP chemistry test, but it's a graph that relates the velocity of particles to the number of molecules that have that velocity. So first off here, we're comparing or looks like we're comparing the same substance at different temperatures. So we have a substance at 100 Kelvin, the substance at 300 Kelvin, and the substance at 500 Kelvin. And this graph really does show how temperature is related to average kinetic energy, because you can see that they are all bell curves. Even though, say for this here, the sample at 100 Kelvin, not everything is at the same velocity, even though it's all the same particle. And the kinetic energy equation would tell us that if we have the same mass, that we're all going to have the same velocity. But just because it's at the same temperature doesn't mean that every single particle has the same kinetic energy. We're looking for sort of an average here. And we can see that there is an average. There is a point where most of these particles or molecules are going to have the same velocity, but we have a spread. There's going to be some that have less and some that have more. And this is just naturally how this works. You're never going to have every single particle in a sample with the same amount of kinetic energy and therefore the same velocity. And you can see as the temperature increases, the spread gets bigger. We're always going to have some particles that have lower velocities, but our bell curve kind of like gets squished as we increase the temperature. And you can see that the average point, even though the number of molecules at that average is getting less and less as we increase the temperature from 100 to 300 to 500, there still is sort of a average point in the middle of the bell curve that represents the average kinetic energy of the particles, and therefore the average velocity of the particles. And as we get here at 500, this is super spread out, so we have a really wide range of velocities at higher temperatures. We end up seeing a similar sort of graph. This almost looks like the exact same graph, but it's actually representing something different. When we are comparing things with equal kinetic energy, so last time we were comparing things that had different kinetic energy at different temperatures. If we compare multiple substances with different masses at the same kinetic energy, we'll see that we have a similar impact. So here we have xenon, argon, and helium. So based off of that equation of K is equal to 1/2 mv squared, we know that there's an inverse relationship between the mass and the velocity. So as the mass increases, the velocity is going to decrease. And in this case, all three of the samples of xenon, argon, and helium are at the same kinetic energy. We're at the same temperature. But we're going to get different spreads of velocities. So xenon, our heavier particle, which is going to have a lower velocity, is also going to have a lower spread of possible velocities. Much like the last graph, we have some that have a little bit less and some that have a little bit more, but on average, most of the xenon particles are moving around the same speed. As we go to argon, something slightly lighter, we spread out our curve a little bit. We still have an average around here, and the average is going to be higher than the average for xenon. And then for helium, our average is going to be even higher as well, but with more of a spread. We have helium particles that are moving really slow, and then helium particles that are moving incredibly fast. So the main idea here is just to remember that for the temperature is related to the average kinetic energy. As the temperature increases, our possible velocities are going to increase because the kinetic energy is going to increase. And then the possible velocities are going to be related to the masses of the particles. So as the masses of the particles increase, the velocities are going to go down. But one trick question that sometimes pops up on the AP chemistry test is something like, how did the average kinetic energies of all of these particles relate at this temperature? You could always say that they're more or less the same because temperature is average kinetic energy, but the thing they will differ by is their velocities. So keep that in mind, and I'll see you in 3.6.